I'm going to look at a question that tests the analysis part of F324, and it's all based around esters. So the question starts by asking a fairly straightforward question about the preparation of an ester. It's from propanol and ethanoic anhydride, and you've got to come up with the equation. The analysis part of the question starts now, and it starts with testing your knowledge of gas chromatography. So we've got a mixture of two esters contaminated with an alkane and an alcohol, and they're going to use gas chromatography to separate. And the important thing is that the stationary phase is a liquid alkane. So recall question first, how does a liquid stationary phase separate? And then the second part of the question, how well do these four compounds get separated using an alkane stationary phase? And the main part of the question now is a big analysis question where they ask you to work out the structure of an ester. And you've got to use all of the information given. So you're given some analysis by mass. So we'll be thinking what you could do with that. You're given a mass spectrum, and you're given the proton NMR spectrum. And just look at the information given. Obviously you've got the shift value here, and you've got the peak area, and look at the splitting patterns. So you've got to come up with an identity for the ester and obviously show your reasoning, and we need to use the appropriate technical terms spelt correctly. The equation, we've got ethanoic anhydride and propanol making this ester here and ethanoic acid. So just remember, when you make an ester from an acid anhydride, an alcohol, you get the ester and the carboxylic acid from the acid anhydride. So ethanoic anhydride would make ethanoic acid. I'll just show you what I've got scribbled on the blank page. So this is just the displayed formula of what's gone on, and we use this simple lasso here to create the ethanoic acid, and you can see the esters formed by joining the two parts together. So that's what the ester would look like. The gas chromatography question, so how does a liquid stationary phase separate organic compounds in a mixture? Well, basically you've got two types of separation in chromatography. If it's a solid stationary phase, it's by relative adsorption. Well, we've got a liquid stationary phase here, so it's relative solubility. And then the sort of tougher part of the question, how well do these four compounds get separated using an alkane stationary phase? And the easiest way to think about this is like dissolving like. So we've got two esters, an alkane and an alcohol. And you can see I've scribbled up here, the two esters are going to have the same polarity as each other. The alkane is non-polar and the alcohol is polar, most polar, I've said there. And so think about how these compounds are going to interact with an alkane stationary phase. So if we deal with the alkane first of all, like dissolves like, so that's going to really like the alkane stationary phase, and so that would slow it down and it would have the longest retention time. The most polar one is the alcohol, so that's not going to interact at all with the stationary phase, and so that would go through very quickly and have the shortest retention time, and the esters would be somewhere in between. So how have I written that up? Esters would have similar retention times due to their similar structures and therefore similar solubilities in the stationary phase. The alcohol would have the shortest retention time because it's polar and won't be very soluble in the alkane stationary phase, won't interact in other words. The alkane will have the longest retention time, it's non-polar and will dissolve fully in the stationary phase. The big analysis part now. So we're told that it is an ester in a perfume. It's separated by gas chromatography and then analysed. So you can see I've written here, with this information here, we can calculate the empirical formula. So these are just little things you should be thinking as you're reading through the question. The mass spectrum, see I've just circled the peak furthest to the right. This is the molecular ion peak, and that tells us the MR is 144. And I would write that on the spectrum as you're just processing the information, because the examiner can mark it. And then the big thing here is the proton NMR, and I would be writing this in the exam actually on the spectrum. So let's start here. We've got a peak area of 9, so what does that mean? It means there are 9 equivalent hydrogens or protons in this environment, and the only way really you're going to have 9 protons is with 3 CH3 groups. The fact that it's a singlet means there are no adjacent hydrogens. In other words, there are no hydrogens within 3 bonds. Got to be within 3 bonds to cause any splitting. And the shift value is the RCH value from the datasheet. And then I've highlighted this in blue. Again, it's still RCH. Peak area of 3. So it's probably going to be a CH3 group. And it's a triplet. So therefore it must be adjacent to a CH2. So the next environment is hydrogen bonded to a carbon bonded to a C double bond O, which is one of the environments we'd expect in an ester. So peak area 2, so 2 hydrogens in the environment, so it must be a CH2, and it's a singlet, so there are no adjacent hydrogens. So if you just look at what I've written there, this must be a CH2 group here, and we have no hydrogens within 3 bonds that could split this. And then the pink one, this is the other environment you'd expect in an ester, H to C to O to single bond O. Peak area 2, so 2 hydrogens again in the environment. It's a quartet now, so we must have a CH3 group adjacent to this. And so if you just think about this, we must have a carbon with 2 hydrogens on. They're obviously causing this peak, and next to this, adjacent to this, must be a CH3 group. So let's put all that together now. So there's a little reminder to myself there. It's an ester, so we've got to have this in the molecule, otherwise it wouldn't be an ester. So let's have a look. Empirical formula, straightforward calculation, percentage over the MR. So we get a ratio of 4 to 8 to 1. So the empirical formula is that. The molecular ion peak, so we're using correct terminology there, is 144. So does the empirical formula add up to that? No, it adds up to 72, so there must be twice as many atoms in the molecule, so it must be C8H16O2. You see it's still got that ratio in it, but there's twice as much of everything. So the structure, well, there it is there. So if I just explain that in terms of the spectrum, so that singlet at the far right hand side is due to these protons here. You can see there's 9 of those, and it is the RCH environment. We've got the green ones now, and remember that was a singlet as well. I'll just show you again. This one here. So that's a singlet because there are no hydrogens within 3 bonds that could cause splitting. So there's 2 in the environment, and it's adjacent, or bonded to this C double bond O. And then the pink one, we've got the 2 hydrogens in the environment, and they're bonded to a carbon that's then singly bonded to an oxygen. So that's the other ester environment. And remember that was coming out as a quartet. and so we've got a CH3 group adjacent to that. And then the final environment, this is another RCH environment, and that's coming out as a triplet because it's adjacent to this CH2 group.